So today we are very lucky. We have three exciting speakers coming from different, who are people affiliated to different space agencies from different continents. And I'm very happy to introduce the first speaker, who is Vandi Verma, Dr. Vandi Verma. She's the Deputy Section Manager. Welcome, please. Yeah. I'll just say a couple of lines. She's the Deputy Section Manager for the Mobility and Robotics Systems at NASA Jet Propulsion Laboratory. She's also Chief Engineer for Mars 2020 Robotic Operations. I'm pretty much everybody know about that, but she has been engaged in Mars operations since forever, like Spirit, Opportunity, and after that Curiosity, and then Perseverance and Ingenuity. She's going to give a talk on the usage of Perseverance and Ingenuity helicopter on Mars. Yeah, thank you.
Thanks, Arjun, for the introduction. It's funny. I like the name. My son's name. You have the same name. Oh. So that's great. So today I thought I'd talk a little bit about the first missions where we ended up with a rover and helicopter in a mission. It was sort of an accident that we ended up using them for so long, and I'm going to go into some of just how we actually found the benefit in using the two together, and some of the challenges, and what things we can do in this area. So to start out with, the Mars 2020 mission, which is the Perseverance rover and the Ingenuity helicopter, the purpose of the mission really is to look for signs of ancient life. We know Mars had water, we know Mars was habitable, and this next mission, scientists, hundreds of scientists from around the world get together, and they're trying to go to a place where there's a really high probability there could be life. And, I will try to be closer to this. And if you're going to look for life, one of the areas where you're most likely to find it is in a delta. So Jezero is a delta, and a delta can sort of be teeming with life. And that sort of was where this mission was headed. Getting to that location is in itself a challenge. So one of the first things when we deal with multi-robot missions is getting to another planet is a packaging problem, essentially, in the beginning. So thinking about these multiple robots, you really do have to think about how you're actually going to put them all together. And mass is a big constraint. This is one of the reasons why multi-robot can be challenging, is you really have to have significant value from adding the second asset over just having one in order to do that. So here I'm showing a picture of the various stages of the Mars mission. So on the top, going from top to bottom, that's the cruise stage. There's a back shell, there's a descent stage, and then that's the rover. And in order to fit in, and then there is the heat shield. In order to fit into the rocket, you really have to do some robotic origami. And that there was the Ingenuity helicopter. It had to be packaged and strapped under the rover to make it to Mars. So really, this is one of the aspects that sometimes you work in multi-robot systems and you don't think of. You're like, how am I getting to the other planet? That is a huge aspect. And it might change your design, which can have implication on all different aspects of the robotics. And then this just shows, once we had that, you saw the helicopter, we were literally going to land on the surface with the helicopter bottom first, with all the debris coming up and the retro rockets firing. And some of you may have seen the video. It had to be protected. This thing weighed 1.8 kilograms, very delicate. So there was a debris shield, and there was also a belly pan for the instruments that was going to collect the rock samples. But we had to go really drive far away, deploy that, because the helicopter's navigation cameras, when they were going to do their first flight, there was a concern that the reflection from this could have impacted the navigation. So these are the sorts of things where once you've built it, you realize, can the reflection have an impact, and am I going to crash land on the first flight? So there was a lot of things that you sort of are the side effects of it. And this is how it was under the rover, connected to the rover, being powered from it. One leg at a time, we deployed it on the surface and from the belly of the rover and drove off of it. So that's kind of how Ingenuity made it to Mars, and we ended up with the first rover and helicopter on Mars. It's actually been a very successful mission. So there's a risk when you add a rover, because one of the things we were concerned with, if it doesn't drive off, you've now got a helicopter strapped under the rover. It can impact the main mission as well. So at this point, we've collected 27 samples, and Perseverance has largely been an autonomous mission. It's a significantly more autonomous than any prior Mars mission. And this is with a lot of updates that were made in the computing and in the algorithms for Perseverance. It's driven at this point about 27 kilometers, and we've had rovers on Mars for a long time. And you'll see in other, I don't have it in this case, but you see the leap we made with this rover was quite significant. Even the previous rovers, opportunity for decades had been the rover with the longest distance. And these distances are challenging because you're driving in terrain that we really expect and have some estimates from the scientists, but almost always there's a surprise. Like with Curiosity, the wheels ended up getting holes in them because the rocks were really tiny, not obstacles from a navigation perspective, and really hard for perception to distinguish whether it is a point event effect, but those are some of the challenges you have to work around too. And the helicopter has logged 72 flights. It was supposed to have just 5 flights, and so it's been very, very successful to have the helicopter. So I was going to next switch a little bit into like how, given that we ended up with this helicopter that survived for so long, we had the ability now to experiment with how we can use this for a rover mission. It was, the original intent was that we would deploy it, it would do its first flight, do a few more flights, and then Perseverance would drive away and do the rest of its mission and would have nothing to do with the helicopter mission. They were sort of serialized in intent. But it ended up that because Ingenuity was coming along, there were ways in which we can use it. The first one will be one that many people would think of, right, is the aerial scout. You have this rover that's carrying, over 100 kilogram of payload, and you want to deploy it where it can go. You don't want to drive in every direction. So you can see on the top left there in the picture, there's a tiny rover. That's a Perseverance rover. It's like if you see it, it's a little picture of the rover right there on the top. This is a picture taken by Ingenuity of a crater of Belva crater, where we were looking to see should we go there. And we were able to take this, and the scientists saw some really interesting features, but they also looked at it and said, it's actually not that different from places that we've been to. And so we were able to carry on along and make more rapid progress in a direction that would have more promising signs. So this is when the helicopter flights are minutes. And I'll go into some of the challenges with that. So you can go off and scout multiple locations if you were to do this long term. Now, Ingenuity, because it was a technology demonstration, and by this time, it was very long into its mission, so it had to recharge for a while. So we weren't able to really deploy it as frequently. But in the future, if you address some of those challenges, you can really do that. The scientists were overjoyed every time they see a new location that is inaccessible to a rover, and you're putting it at risk, putting it there. They just are. And it also raises the potential to, in the future, we would want to access locations like that. This is an example of what you could do in the future. We didn't have this as Ingenuity, but this is, if it had survived even longer, we were actually thinking of doing things like this. So this is a picture taken from Perseverance with a wide-angle camera. So it has navigation cameras that are used for navigation, and they're wide angle. And they are color imagers, but for this purpose, we take a black and white image because it's lower data volume. In this image, you see it doesn't look very interesting, right? It'll take this image and look at hundreds of features and then detect what's the most interesting thing. And this becomes really important as you're driving really long distances, because you're not going to stop and no human is going to look at this. It's just the rover driving along and taking pictures. What we do with the rover right now is we take this picture, we figure out what the most interesting rock is, and this was, I think, Sol 460, where it picked 2, and then we have a telescopic imager, and it has a laser on it. So we shoot the laser at that feature, it creates a plasma, and you can study the properties, and you take an image with the RMI imager. So you can get really detailed imagery of the really most interesting rocks in a very, very scene that might not have a lot of other interesting features. It would be really great to do this with the aerial asset. Now, doing it from above and giving the scientists, so see if you were to go in, direction 1, you're going to get this. If you go in direction 2 or 3, and then they can really look at this kind of really detailed information. Whereas they're doing it, at a very coarse level right now. So this is the sort of thing that we didn't get to do, but we would love to do in the future. The other part that is really great if you're going to have a heterogeneous system is the different perspectives, right? The aerial robot really offered us some really good perspectives. So I'm going to show you another example. So this is an actual drive. I don't remember if I was on it or not, but these are the tools we use, and we have to use images from Mars. This is taken by those same navigation cameras I was talking about. There's occlusions. The rover's mast is, 7 feet tall, but still, when you're looking at the far distance and you've got free-form terrain, you're not going to be able to see past near-term occlusions and hazards. So we have a lot of holes in our meshes. We have a lot of holes in the data. And as we have frequently discovered, because it is Mars, it can look benign, but they can be rover-killing hazards in some of these locations, so you don't drive in areas that you have no perceptual knowledge in. So this was sort of one of the wins, and the scientists really wanted to do the drive at that sol. This is the other aspect that's really interesting in planetary science is you have data links at particular times. You have holidays, you have other things, and they really want to get it at a certain time because it would mean they have the data to process on Earth and then go on to do some scientific observations. So they really, really wanted this, but we were like, this would be challenging. So the helicopter, RTE, so the helicopter had navigation cameras that looked down. They put a second camera, it's a color camera, it's called RTE, the Return to Earth. Interesting, those were imagings that were meant for Earth, for people, scientists to look at, that's why. So this was the mesh from the helicopter image. And you can see, because it's looking top down, there were no occlusions. And so this was really useful. What's challenging is these are the sorts of things where you're like, theoretically, these things are not challenging, but it's actually not trivial to register the helicopter image with all the uncertainty in its post-knowledge and the rover. So we actually don't have that, but it was still very useful. That is something that we actually have a proposal and some students working on, but it is something, the way we are doing it is we are registering the rover images to our orbital map and the helicopter images to our orbital map, and so they can have knowledge. But that's not sufficient, because for the rover to drive, you need it in the rover's coordinate frame, and with a very, very good understanding of the uncertainty. And so this is the orbital mesh. So we do with some planets like Mars, we've got orbiters around Mars. So we have the advantage that we have sort of an orbital map. And we don't drive in those maps because the rover's position is very uncertain. But you can look at hazards, but it's very, very coarse. And so this was the drive we actually ended up doing. And the reason we were able to do it with the helicopter images, so you can see there's all those sand dunes on the left side. This is actually a tool we use to visualize the navigation camera images with the middle wheel tracks. And we skirted this area of sand because we still use visual navigation. And on sand, it's very variable how much registration we'll have and how the stereo will do. And if the stereo is poor and you're trying to autonomously drive, you're going to get a lot of wandering all over the place, and the rover may try to divert and completely skirt around and go in a direction that is not intended. So we still have a lot of challenges with sandy terrain, and Mars is all sand. So that is a continuing problem. So we were able to do it because of that. So this is an advantage that if you have an aerial vehicle, the different perspective complemented with the surface vehicle is a huge advantage. And then the last one I was going to touch on is the variable risk posture. So this is another really big advantage we have with Ingenuity. It was a technology demonstration. And we could take risks there that you cannot take with, $1 billion+ rover, which has to meet its science requirements. So Ingenuity pretty much had off-the-shelf parts. It had a lot of things that you use in cell phones, and because it had to be lightweight, it just had to weigh so little. It weighed, 1.8 kilograms. And so used Qualcomm, actually, Snapdragon for the processor. And you can literally see, this is a slide that one of our interns helped make. So it was like trying to get the point across, right? Huge difference if you look at, the compute speed and just the memory. And the radiation-hardened processors that you have to use if you're trying to meet the requirements for being able to not have resets in these really high radiation environments. They are really, really, like it's really slow. So now we had this advantage is the risk posture can be really small. You can take risks. And so we had this great computer. We've got a lot of things we're trying to do with this, but I'll tell you about the first one. And the first one is, so there's a computer on Ingenuity, but there's actually a second computer on the rover. So it's called the helicopter base station. In order for the helicopter to talk to Earth, it really doesn't have the power to talk directly to Earth. So it talks to the rover, and the rover transmits to Earth. But to talk to the rover, there's an antenna, and that has a Snapdragon in it as well. So the rover is carrying around for the helicopter this other computer. So what we did with this was we said, how about if we use this for global localization? As I was saying, we don't actually know where the rover is on a map of Mars. So there's no GPS, and as the rover is driving, as many of you who work in pose estimation, it's sort of losing its estimate of its position. And this is a problem we've created for ourselves by driving really far. With autonomous navigation, we are now driving 700, 500 kilometers, and the rover is, by the end of that drive, it can be off by quite a bit. So we are limited. This is one of the limits for why we can't drive any further without Earth in the loop, is because the position knowledge. You're trying to get to a scientific target. You do not want to be 32 meters off of it, things like that. So there's a paper at ICRA that we have, so I'm not going to go too much into it. Jeremy's presenting it, which talks about the global localization algorithm in this, and that's on Wednesday. But I just want to hint at why it matters. So if you look at, this is an actual drive we did. It was a 700-meter drive. We were at the base of the delta. This is the delta you saw. We're climbing up to the top of the delta. And it was done on a weekend. So when the rover initially lands, we are on Mars time, but then slowly we start to get onto Earth time. And we take our weekends off. And so this was a drive we did on a Friday so that we could come back on a Monday. But look at the position uncertainty. Now, this is not real. It is a lot of what the algorithm has to track. But that means that is something you have to account for. And the little red there is Ingenuity at the time, right? We wanted to, these are these hazard maps we need to keep our distances from. So, I'm going to end with some challenges. So there's a lot of advantages in having multiple complementary assets with different capabilities. So one of them is, the latency. So the way we currently do communications with Mars is there's a huge time delay, 24 minutes. It can vary to hours depending on where the position of Earth and Mars are. But we send the commands to Mars for what both the rover and the helicopter would do for the entire day or for multiple days, like a whole weekend. So you don't actually know whether the helicopter is going to have a fault and do an emergency landing or where the rover is going to drive. You have to account for all the possibilities when you're sending it. So this is an example I show. There's a little picture. That's how small Ingenuity looks in the images on the top, not very different from a rock. And we really don't want to drive over the helicopter. So that's one of the challenges. You're doing both of these. Both of them have uncertainty. Both of them have errors. But you really don't want to collide. So that with multiple robot assets, that's a very practical challenge that we end up having, which causes lots of interesting constraints that one also needs to track. And the other one is, this is a video of the flight 47 once we were on the Delta. But you're seeing Ingenuity, it's right here, and it's taken off and it's flying. This is an image captured by the Perseverance cameras, right? With all the uncertainty with mechanism motions pointing a mass to actually take that image. And it's a really short flight. So these are coordinating this kind of imaging was also quite challenging. You have to actually predict what is going to happen and take some iterations by taking still images and the focus to get those images. So there, is sort of Ingenuity flying. So that was some of the practical challenge. The other one is, things like Ingenuity was powered by Perseverance while it was attached to it. But once we dropped the helicopter, it was going to have to generate power from its solar panels. And this driving off of the rover, it ended up becoming quite complicated because if Ingenuity hadn't, we hadn't driven off of it and it had detached and stayed under the rover, it would essentially have died because it wouldn't have had the power to survive. And so in this, we actually removed all the faults and checking on the rover's drive itself and made it simple because you really didn't want to have a false positive on that drive. So there's lots of interesting characteristics of, we actually ended up having a direct communication with it for a go, no go, but there are sort of uncertainties in these kinds of deployments that can actually cause a lot of challenges too when you have multiple robots. And then, the science is such that there's some interesting science on the location we landed, because there was, we were landing and we were headed for the center and we had autonomous diverts to the other side, but we were now away from where we wanted to go. And then the scientists were not interested in anything around till the delta. So those are the two locations, and all those markers are showing different types of science measurements. But Ingenuity, when we were driving around, it actually wouldn't have been able to keep up with the rover. So this is where you're seeing it took a direct path across and the rover had to go across. So if you have something where you're relying on one vehicle in a multi-robot scenario to communicate to Earth, you also have to track that they may not be able to keep pace at the same rate. So this was another one where we had to make sure that each point as they were driving over a few weeks, they had to make sure that the helicopter could still communicate with Earth as it's taking a more direct route in order to make it out. So, and then, this is the case where Ingenuity, the Martian winter, so the Mars, year is 2 Earth years, it started to get really cold and got really cold, so it froze. And literally the avionics froze. And it would come back up, but it had no idea of the time. And the way the rover and helicopter talk is to coordinate what time it is. And so it didn't know what time it is, so we had to hunt for it. So we still flew it like that for a year almost, I think, where we would hunt for it, find it, tell it what time it is, and then do the flight at the optimal time that it was. So, there are challenges with using off-the-shelf parts, but, it still survived. It still functioned after that, but they were. So I was just going to end with showing where they are right now. So this was the start of the mission. At this point, the rover, we are headed off to the crater rim, and Ingenuity, crash landed in some dunes to the north there. So we are still communicating with Ingenuity right now, but soon as we start to get off the crater, we won't actually be able to talk to the helicopter, but we've set it up so that it will keep waking up, so that we are supposed to come back to the crater to rendezvous with the next mission to launch from Mars the samples that we've collected. It's possible that we will see if Ingenuity is still alive and available for that. So that's all I had, and we put some contact information, but you can also reach out to me. We have a lot of the work that we've done with some of the interesting new capabilities was actually done with a lot of students and postdocs, so we do that a lot. Thank you.
Thank you very much for the inspiring and fascinating talk. Are there any questions from the audience?
Great presentation. It's such an inspiring work. So congrats. It's very inspiring. I know that Ingenuity stopped working, stopped flying essentially last January. As far as I understand, the failure was in the visual inertial navigation system. Do you have thoughts about that or lesson learned that you can share?
Yeah, so I think, one of the interesting things about it is that the challenge was with the navigation and how much of adjustment it tried to make as it was coming down to land. And, that's one of the things that's been very interesting is they had already accounted to the fact that when it comes down, it actually stops using certain sensors versus others as it's coming closer to the surface and it's dropping. So I think this is a feedback for the landings are actually quite interesting, and that's where also you have the most risk. So I think you're absolutely right. There would be quite a bit of work to look into how do you integrate the sensor knowledge and what is the uncertainty and estimate of it. So I think that is some of the work that, and actually there's a lot of data now. So I can imagine this is going to be a rich area where you can use that data to see if there was, tracking some of those challenges. But yeah.
Hello, thanks for the presentation. I have a question about the autonomous navigation. You said something like 95% is autonomous, right? How did you choose the 5% that were not autonomous? Did you have an idea of where the danger spots were or the risky places? I don't know. How did you choose those places?
That's a great question. So we actually, every day when we decide to drive, we have, and I didn't show the chart in this presentation, but I might, there's another TC Forum thing I'm doing and I might show it there, is we make a decision, how much autonomous capability we're going to do. Are we going to tell it exactly where to drive? It's never exact. No drive you ever plan ever actually executes because of the uncertainty and slip. Or are we just going to do visual odometry, or are we actually going to autonomously navigate? And it has a lot to do with what we expect the perception system to do and how much it's going to wander and get stuck. Because we allow it to retrace its path in order to go around some hazard. But there are cases in which you could just end up further back from where you started because it's trying to make its way through and it got stuck and it never made it. So the decision is, and we are in a very challenging terrain right now, and you're like, autonomous navigation, the capability we have on the RAD 750 right now is not capable of handling this challenging terrain, so I'm going to navigate with humans in small. But you also make progress in shorter distances. So in a day, you can't go beyond what you already see in the previous images it's sent back to Earth. So it's very limiting. But yeah, it's made by humans, that decision.
Okay, I have a last question. So JPL people are great doing robots and make it last longer, much longer than expected. And I want to know, how was this decision of having a Snapdragon in the helicopter, because that, I guess, is quite risky because it's no radiation. And the second question could be, are you going to rely on a Snapdragon in the future missions, or fully rely on a Snapdragon?
Yeah, no, that's a good question. So I think one of the things is, so when you have something has to last a certain amount of time guaranteed, you really have to build for more than that because there's uncertainty in what will last. So this is why, if you want to guarantee, you're going to over-design a little bit beyond that so that it lasts. The Snapdragon was all, and why it was, there was a lot of other areas. We were working already with Qualcomm in other areas, but I think it was essential. You could not meet the weight requirements and the power requirements. And so this was a case where once you start to design certain missions and you need to be really light, it was a trade-off where there was almost no choice. But now that we've seen its behavior, we are looking into future missions, in fact, that the computer is absolutely essential. If you look at anything with robotics, anything with perception, you need the computing power. The challenge becomes, how do you do the trade-off? So there's actually, I don't know how many discussions we've had in the last few months about what is the right architecture here. And I think this is a very, very active area of discussion. So we haven't arrived at a full conclusion yet, but it is one of the highest discussion points,
Okay, thank you very much again, Vandi.